All right. I think we're live, so we'll just have to keep our fingers crossed. Hopefully, everyone is here. So, welcome. It is now 12 o'clock, and it is time for Tech Art Talk Live. My name is Chris, and I'll be your host today. And today, we are going to be going over the rendering equation. I'm sorry, you probably are going, like, what is the rendering equation? I mean, like, I've been doing this CGI rendering since I've been in high school. Yes, you have, but there is a new evolution of things, and you might be aware of it, this whole thing about PBR and so forth and ray tracing. So they all have a commonality, which is called the rendering equation. And so what exactly is this rendering equation? That's what we're going to be going into today. Okay, so if you have any questions, please go ahead and come on in, drop me a line, and I'll try to pick up on your question. And if I can't, please go ahead and submit your question to me at uh, at any of my points of contact at Chris at techartedu.com. I should be able to answer your question, or at the Facebook or on the LinkedIn link, or even on this YouTube channel. I should be able to answer your questions. All right, let's get things started. All right. Now, as mentioned before, we are dealing with PBR, and PBR is, physically based rendering. We went through and we created some interactive demos of it last week, and it was pretty cool. And you know that as far as real-time rendering is concerned now, a way of creating photorealistic images is using physically based rendering. And they've been able to tweak it so that it's real time. So it's pretty cool. And now, what's coming down the pipeline is ray tracing. Now, everyone's heard about ray tracing, and ray tracing has been the elusive holy grail of the industry since about 1982 or so. But ray tracing is on its way and it is coming our way, and you better watch out because real-time ray tracing is going to be everywhere within the next 5 years. Now, if you know anything about the rendering pipeline, it's going to change with with ray tracing, and it's very interesting. And maybe that is a topic for another lecture some other time. But anyway, now ray tracing is going to be real time. And so now how do we make this transition to PBR to ray tracing? Well, one of the first steps is understanding the rendering equation. Now, the rendering equation is the core and the guts of what makes all of this work. All right. Now, last week we gave a little bit of little down memory valley as we looked at traditional Phong lighting. Now here I found this image on the web where we show surface normal coming off of a ball, and then we have an incoming light ray with that yellow light coming out and a golden reflected light coming out, and a viewpoint is where the vector to the camera is located. And so we looked up this normal equation like this. Now this is what normally people create the illumination model. That is the red component, that is the ambient or the default shadow color. The green component is the diffuse or the Lambert element, and that is the diffuse light. And the blue is the specular component. And those all get added together, and that gives you the light of your pixel in the scene. Well, guess what, folks? That is no more. No mas. It is history. And we are about to go on to a new critter, and that is called the rendering equation. Yes. And so before we get into what really is the rendering equation, let me show you what the philosophy of that is. Okay, suppose that you have a light and it is shining on a surface here. And so it is like looking onto that surface, and then it's sampling. It says, okay, what is the amount of light hitting onto this camera? Well, it's actually a combination of the light that this point is actually given off and the sum of all the lights that are coming on and hitting that point, and that point is actually pushing off light into all the other directions. And so this is kind of like based on something called the conservation of energy. And that describes that the total amount of light energy emitted from a point, that's that little point X, along a particular viewing direction, which is like pointed at the camera, and for a given incoming light and a BRDF. Okay, we'll get into what a BRDF is. So really what we're going to do is say, okay, the light coming at the camera is really a combination of the light giving off by the object itself and all the light that it is reflecting. So remember how we were dealing with PBR last week when we said that reflecting is so important, whether the object is metal or non-metal, wood is rough or solid. It's really about how it's reflecting. And so this is actually taking that reflecting component and putting it in action. Okay, so the rendering equation, the simple version of it looks like this. And that's exactly what we were talking about. On the left side of the equation, we have the amount of light that's hitting the camera. And that equals the amount of light that is emitted by the object plus the amount of light that is reflected off of the object. And so realistically, in words, this is what it all means. The light leaving a point X on a surface I in the direction omega W is the sum of the light emitted by and reflected from the surface along omega 0 from the small area around X. Once again, what that means in English is the light hitting the camera is the sum of the light being emitted from the object plus the light being reflected from the object. Those two elements. All right, in its all found glory, this is what the rendering equation looks like. This is what it looks like in its goriness. So let's break this down. All right, now we know we're going to be dealing with some point X on the surface of the scene. And that's what we are dealing with. And so X is on the left side of the equation, and it's on the right side of the equation. Okay, then we have omega I, which is short for omega incoming. That means that the incoming light coming into the point from some other direction other than the camera. Okay, omega 0 is the light that is actually emitted from the point itself towards the camera direction. And we see that it is on the other side of that funny looking squiggle thing. Okay, now we have the N, which is the surface normal. Now everyone knows the surface normal, right? So that should be a familiar term. And then we've got the dreaded integral sign. Now for those of you who understand calculus, you know what this is, but for everyone else, that just means that we are going to consider all possible light rays coming into and hitting that point. Not just one ray, not just two rays, but all the rays. Now you're beginning to understand why this rendering equation takes such a long time. Yeah, so when you're dealing with all the rays, that's what this little squiggly S dealio means, and that means it's an integral of all the directions of the light impacting that point. So let's take a look at it again by the individual component wise. Okay, the first term is what light do I see at the point? You know, that is how much light is actually hitting the camera. Okay, and it equals to the second term, which how much light is the point on the scene actually giving off? Because you know the little object might actually be a light source. So how much light is it actually giving off? And then this third term is how much light is reflecting from this object. What is the sum of all the light coming from this point from all angles? Okay, so let's take a look at this third term, this integral, more closely. And so it's composed of three different components in itself. The first term is for the specific direction, how much light is coming in, how much light is actually coming in to that object. And now the second term, this is the material function. This is the BRDF. And so basically, what a bunch of researchers found out is that when light hits certain materials, well, that light behaves differently. So therefore, every single material has its own specific material function or its own BRDF, and that describes how light actually behaves and reflects from it. And this third term of the integral, actually, you might actually recognize this. That is the incoming angle dotted with the normal. Does that sound familiar? Well, it should, because that's basically the old Lambert formula, from the old Phong equation that we were dealing with earlier, if you can remember back then. That just basically means that the more perpendicular the light source is with the surface normal, the less light it picks up. Okay, so let's look at things a little bit more about what this squiggly means all the light. All right, so if you look at the little s squared and the delta of the omega I, that means we're taking into consideration all the vectors or all the amount of light coming into that point. And there are two axes at which we're working on, and that's the zenith angle, which is coming from down and moving over, and then we have the azimuth angle, which kind of like rotates this way. These are called polar coordinates. And then when we take all of the zenith angles and all possible azimuth angles, we get s squared, which is all possible angles. And so what about this BRDF function? Okay, now it is a function that describes the reflectance properties of a surface. And so it also behaves with the same kind of azimuth and the zenith angles, and therefore it has certain properties. This function gives off certain values depending on what the azimuth angle is and what the zenith angle of the incoming light is. Okay, so here are the properties. So that the light coming into the material is called the irradiance. But when the light is popping out, that's called the radiance. So we've got the radiance and the irradiance. And for a BRDF to be physically possible, it has to do a couple of things. Well, first, it has to obey the energy conservation. That means the amount of light coming in has to equal the light coming out, so that there's no energy being lost or gained. So it needs to be constant. And the incoming and the outgoing are considered as reversals of each other, and they aren't affecting the outcome. So you might be wondering, okay, this is cool. Well, where do we get all these BRDF functions? Well, you can either measure a BRDF or you can model it. Now, a bunch of folks over at Disney, and I've got a couple of links here you can follow on here. They've got all of the BRDFs that you could ever want and need. Now, if you look onto a commercial game engine, the BRDFs for all these objects are actually stored within the engine itself, and so these are taken into consideration within all the materials. Isn't that nice for them? But if you needed to ever create one of these BRDFs for yourself, this is the place to look. Now, if you had access to something that measures the azimuth and the angle, what you could do is, I don't know, is this maybe over at the UCF Photonics Lab or something? I don't know. But anyway, they're going to create a gizmo like this. And this crazy critter here is an object. You put the object right in the middle of that donut-shaped object right in the middle, and then they have a bunch of lights shining on lights as it moves over the arc back and forth, and then they rotate that whole arc a little bit, and then they rotate it again, and they do that for every single angle, and then they measure the amount of light coming off of that object depending on where the light is coming from, and that is how it is created. I threw that in there just because I thought it was neat. Like, how do we create these darn things anyway? Okay, now let's get back to the equation. Now, this is like really complicated, and you can't possibly take care of all of the infinite angles or all of the infinite light coming into a point. I mean, like you're doing the azimuth times the angle, and it's like there's an infinite amount. But here it is. We got it. So one of the ways of making it behave is focusing on where we point our sampling from, and that is where we call with importance sampling. And so what we are actually focusing on, we can decide on which kind of directions we need to focus on. Instead of actually considering everything, we can just focus on just the angle directions that are going to give us the the best feedback for our BRDF, or here in this case, it's called a bidirectional scattering distribution function. So, how's that for a mouthful? What an angle. But anyway, we've got the angle coming in from the light source. And so once again, we're getting back to the material types again. Is the object metal, or is the object not metal? Is the object smooth? Is the object rough? These are the kind of things that really make the light behave differently. Okay, so when it is metal or it is highly reflective, then when the ray hits the surface, it bounces off in the opposite angle. Now, when it hits kind of a glossy surface, then it hits and it kind of bounces off in kind of like a bunch of different areas. But when it is diffuse or it's more matte, and that means it's really rough, and that means it's spattering all the reflections all over the plate. And so different materials behave differently, and so this is where all the angles are going. So what we're going to do is we're going to take that information back into our rendering equation, and then we're going to apply these and look only at specific angles depending on where the lighting is coming from. So if you know where the lights are coming from, then go ahead and shoot rays at it, or actually consider those angles, and focus on those, because that's where you're going to get the most amount of information. And when you focus on the specific lights, that's called multiple importance sampling. So you take your target known lights, and then you apply the specific reflection or the material type, and then from the actual point of that you're actually rendering, then you're going to do more sampling towards the lights that you're actually dealing with. And so, as you can see, it's pretty easy with the mirror reflection, but when you get glossy reflection, you're starting to consume just a portion of the angles being reflected. But when you go into the diffuse, then you're really dealing with just a small portion of all of the possible angles that you're dealing with. And so here's an example of various light sources with using the multiple importance sampling. Now, by default, we ended up with, on the left, all this crazy stuff here, and it looks, okay. Now, you've got the sample BRDF in there, and just by plain direction alone, it just produces some basic, some basic points there and samples. But when you use the multiple importance sampling with a power heuristic, then you've got a good coverage, and you're going to end up with the best looking image. And this is where we start getting into ray tracing, where the engines that we have light maps that are used from, but now when we go into the ray tracing, we're actually going to be doing, instead of accessing those light maps that are pre-rendered, we're actually going to be using the rendering in real time and creating dynamic things. So we're not going to need light maps anymore, but that's what the advantage of ray tracing is coming in. Okay, that is what I wanted to cover with you folks today. And let me get my window back here. Where is it? Okay, let me show you. All right. And I just realized that I gave this entire lecture without seeing any kind of graphics. Okay, well, that is how things go. That's not fun. Okay, I will have to go and repeat this lecture again at some time in the future, or I will go and create a video of this and actually store this off onto YouTube, because this lecture is just about worthless with all the graphics because I failed to show the right window. I forgot to transition things. All right. Well, I'm not going to have a lecture for you folks next week. What we're going to deal with is um, um, Thanksgiving, and I am going to be out of town, and so I am not going to be around to give a lecture next week, and so we'll just have to wait in 2 weeks. And in 2 weeks, we are going to start our conversations on ray tracing. And so ray tracing is a really big subject. And so I think we're going to do 2 specific lectures just talking about the modern implementations of ray tracing. And that is kind of like where we're going to go, and that should be just about where we end up for the year. Now, if there's any other topics that you're very interested, at least in the tech art area, please go ahead and give me, contact me and, ask me more about these questions, and I'll be happy to divulge what I can in the next version of Tech Art Talk. So if you like what you saw today, go ahead and subscribe to the channel. Check me out, Chris Rhoda, on LinkedIn and on Facebook. And if you have an opportunity, swing on over to the techartedu.com website. Check out that website, techartedu.com, and drop on by, sign up for the information, and I will give you up-to-date information of when we have new things, because I'm constantly working on the Tech Artist Handbook. We've got other implementations. We've got the procedural gems coming out. We've got lots of really groovy stuff. And so if you want to be up to date with all the most recent information of TechArt EDU, please contact me. Sign up for the information from the techartedu.com website, and I'll make sure that you kept up in date. All right, thank you very much for your time today. Thank you very much for your patience, and I will see you all in 2 weeks for the next version of Tech Art Talk Live. Talk to you later. Bye.